So, what is spectrum? Anytime someone says spectrum, it refers to frequency domain. And one might wonder, well, what is the frequency domain? Any thoughts? No? Did we not do differential equations?
Long time
We
ago.
did. You can't do
Summer
it.
course.
Huh?
I said I did it a long time ago, and it was a summer course completely online. I learned. I got to go to.
Was it during COVID? Was it during COVID?
Yeah.
I thought you might have been
I
in my class.
mean,
It was on the library. When COVID happened and differential equations.
I think I had B for it, so it was literally just his PDFs that you had to learn off. There was no class aspect.
But I had asynchronous bachelor's. I just couldn't. Okay, Fourier transform. Do we remember Fourier transform? I won't get into too much math about this because, you know, there are some non-math students. But start with a simple example so you get a good idea. We all listen to music, right? We like music. And music is in the time domain, so easier ways to recognize from hit play, MP3 plays, say 3 minutes and 23 seconds for that song, right? And if it's a Nicki Minaj song at all, I do like a couple of songs there, got to say. That's something, it's more like a time series, but time domain, you're going to see something like that, right? But if someone asks you, well, what are the frequencies that you hear in that song? Musicians, is there a musician here? Or someone playing an instrument? What do you play?
Yeah.
Yeah, okay. You play guitar. Guitar, and when you play music, you've got to pick notes, right? Are the notes the same? What's the difference between F and F minor?
The lower pitch.
Pitch frequency, right? So the way that the sound is at a different frequency range. So use the word pitch, we will get to that in a second. So what is the signal that you have in the time domain? You can convert it to the frequency domain. So what are the peaks that I see in the frequency domain? Well, that is the dominant frequency, and that is the second frequency. So if Andres plays, you know, a particular tune over a tiny time period, I will know what frequencies are in that particular tune that Andres played. But there is a direct connection between time domain and frequency domain. If you can go from there to here, you can go from here to there. It's just how things work. Pitch. What is pitch, Andres?
Scientific, we have no idea.
No, I mean just from the musical perspective.
Things have like higher pitches, things have lower pitches. So,
Well, what is a higher pitch? What is a lower pitch?
I guess frequency, is that the same thing?
I think they are slightly different. Metronome. Did you use the metronome? Okay. Don't you keep pitch with respect to a metronome or a beat with respect to a metronome?
Yeah.
the beat, right? Okay. The beat is with a metronome and you keep, taps on when the change, etc. The pitch part would then be the frequency. And you repeat a tune with a certain beat, right? And that is going to give you the period at which you repeat, correct? So if you have a song, the same chords, the same combination of chords will happen over and over again. Do you agree? Pretty much every song, that's just how it goes. So that beat is what we call a period in signal processing in time series. So during that period, you have a particular frequency for up, a particular pitch. So there is also a connection between the period here and the frequency that we see there. Okay, that's a signal processing way to look at things. Well, how does this apply to time series? Well, time series is a stochastic process, and a signal is also a stochastic process. I think I did a good job. Let's say that is the fluctuation of something over time. And if you look at that picture, I see repetitive behavior. Do you agree? Clearly, there is a repetitive behavior, and that happens with a specific period. So I'll call that period as T. And in terms of time series, that has a specific name. We call it seasonality. Why do we call it seasonality? Because oftentimes time series pop up in weather patterns, stock index, etc. Since weather changes over seasons, like fall, summer, etc. And the same if you have flu, for instance, changes over season throughout the year. When it comes to time series, people like to call it seasonality. This is a series that has seasonality. In addition to that, it's got another bit. What do you think in terms of a weather like this for a reason?
There's an upward trend.
There is an upward trend. Right, so you've got a trend part, and in addition to the trend, you've got seasonality. So when we model an AR, MA, etc., we will pick out the trend part easily. The seasonality part needs to have another component that has to be modeled separately. Well, math people, what comes to your mind when I say period and, behavior that has a period?
Sine, cosine.
Very good, and he's not in the math later. Yes, he is. But you are. Oh, I take that back bit.
Very bad.
sines, cosines, dot, dot, dot. And we need sines and cosines to express the seasonality part of things. So the trend part is going to be fitted using ARMA, and the seasonality part would require sines and cosines. There is another type, of time series. I guess it's slow, did a good job. It does have a behavior that is very similar to seasonality, correct? But there is a key difference between this one and that one. Did you take college? This time series is not seasonal. Sort of repeats, but this is cyclical. It has a cyclic behavior. You don't have the same period. Oftentimes, cyclic time series are a bit more complicated because you've got to model each time period. So first, we've got to identify the time period, then within the time period, if there is a periodicity, you've got to model that too. Good? So, we've got time domain, seasonality plus trend. There is a trend here also, cyclic. It's called irregular period. And of course, you can bring that to the frequency domain also. So one must know how to go from frequency to time and time to frequency, because a sine wave, if you have to model things using a sine wave, you've got to know how the wave changes. For instance, sine wave number one. Fully drawn sine wave number two. Should have used a different color, but the ink is just popping up, so dotted lines. Good enough. What is the difference between the solid sine wave and the dotted sine wave?
The period.
The period. So the periodicity of that sine wave is shorter, the period of this one shorter than that one. So it goes back really fast compared to the first one that I drew. So Sydney said the period is different. Well, the first one, it does have a short period, yes. And it's going really fast. So more frequent. So if I have a short period, then that would imply high frequency. If I have a long period, can you think of a note that has, you know, a very low frequency?
What's the left side of the piano?
Huh?
Go further left on the piano. the
Yeah,
note.
then further, when you press, it kind of keeps on going for a bit. Right, capacitor on this side of the piano, there's like a drag on that side. So long period would be low frequency. And we know how low frequency sounds more big, right? And what is that word that I'm looking for? Not alto, it's baritone.
What was the question?
What is that sound, specific sound? High frequency is alto. Frequency range.
Oh, treble and bass.
Yeah, that's the one. So more bass here and therefore treble. Good. So depending on the period that we see here, I'm going to have a connection to the frequency. So the relationship between time and frequency is short period, high frequency, long period, low frequency, and if you have to put it in terms of math, how would you write it? The relationship between F and T. Come again?
1/frequency.
Very good. Time would be 1/frequency, and frequency is 1/time. Good. I'll wait clear with this part because I'm going to make a connection soon. Okay. So don't forget that. I'll wait clear. Yes. So in the time domain, if you have sines and cosines, what is one full period of a sine? 2 pi. One full circle. But if I have to move a bit faster, in other words, I've got to use a different period. I need to bring time into this, correct? So instead of moving 0 to 2 pi, if I've got to say make a rapid move, I need to sample more points here. So I can write this in a generic way as 2 pi divided by the period. Right? 2 pi over t. This in the time domain would translate to the frequency domain. For 2 pi f. Good. So 2 pi over t means that you see in time domain directly connect to 2 pi f in the frequency domain. Good. There are multiple ways you can learn between time and frequency domain. Long time ago, there used to be something called a discrete cosine transform, then there's the Lord transform, but then came something called discrete Fourier transform. and a faster implementation of it is fast Fourier transform. What does Fourier transform do? It takes time domain and put it in frequency domain, that is all. And when we make that move then, we have time t, or I could even do it as 2 pi over t. But when I move to frequency domain, I've got to pick the frequency somehow, correct? So I need to have sine and cosine play a part there. I'm explaining this in a very basic way so that I don't confuse people, but there is more to this. So I would like to have sine and cosine on this side from last time. How do I get sine and cosine on that side?
You have some e to the ti. Can you convert it?
Last time, what did I use last time? Did I use theta? E raised I theta, Euler's formula could be plus, minus, doesn't matter. I'll use plus for now. The theta part would simply become 2 pi f because we are in the frequency domain. And this is simply cosine 2 pi f plus I sine 2 pi f. Good. So we move from time domain to frequency domain. Of course, this is not just 2 pi over t, perhaps there is a sine, a cosine, sine times cosine, who knows? But there is some periodic function on this side where the period is defined by t. If t is 1, it is a regular sine wave. It is going to move over here in the frequency domain and it becomes that. Good. How does this all work? Or how does it relate to spectrum? Time series spectrum is simply frequency spectrum. What is the most important function when it comes to time series? True. But if you want to learn anything about the transfer function, we need something else. We need to exploit the fundamental behavior of a time series. How are the times related? That's my hint. So, what function is most important? Autocorrelation function. So, when it comes to time series, we've got autocorrelation, autocovariance, doesn't matter. We have gamma, and we did derive an expression for gamma, and we wrote it in terms of the transfer function. I'm moving away slightly from sine and cosine, whatever, here to this because we're dealing with time series. What is important in time series? The autocorrelation function. And I just want to move over there. We have used the backwards operator, the forwards operator, backward shift, forward shift. But the backward, forward shifts are simply items related to time, to with. B times t is just t minus 1. B squared times t minus 2. So that's a time component, We move it over here. I'll still have that constant sigma squared A. Time there changed to frequency here. So e raised I 2 pi f. Times psi of e raised negative I 2 pi. Good. I'm going to do something weird, but there is no meaning behind it. You can tell me what. I'm going to put 2. Any thoughts on that? Why we have that 2? It has something to do with gamma and the lab parameter h. That is my hint. We know that gamma sub h is the same as gamma sub minus h. So it is symmetric, but I typically look on the positive side, I just ignore the negative side. But when we look at the spectrum, we've got to bring it to the right hand side. So it is symmetric. So that's sigma squared A, or sigma of A squared times this part gets multiplied by 2. But just to get the half spectrum. And there is a limit over there, which is 0 less than or equal to f, less than or equal to 1 over 2. Do keep in mind, this is something that we use in time series. In terms of signal processing, the way we represent frequency domain is slightly different. That's not some stuff. Good so far. If psi of b, the transfer function, has, say, sine 2 pi over t, that part will be picked off over here. Agreed? So if I want to know and fit the seasonal component, then I need to know the frequency of that seasonal component. Good. Oftentimes we don't have, well, we do have the original series, we have the autocorrelation function, but sometimes you may not be able to recognize the period exactly in the time domain. But when you move it to the frequency domain, you'll be able to pick it up. Good. That spectrum, or that expression, when you do absolute value, that absolute value sign with complex numbers stands for, from last time. It is simply the magnitude. And the magnitude part would be the square root. So I'm squaring on both sides. And the magnitude of this and the magnitude of that, they are going to be one and the same. Do you agree? The magnitude of a complex number and its conjugate are one and the same. So a plus ib, a minus ib, regardless of which one you're looking at, the magnitude is magnitude squared is a squared plus b squared. Yes. So the magnitude doesn't change. The magnitude of that times the magnitude of that, you get magnitude of that one term squared. Good. So this expression evaluated at different frequency values would simply form what we call the frequency spectrum. Time series people like to call this the period graph, because it gives you the period. If you Google this, you might encounter something called a power spectral density. That's a signal processing term. I say tomato, you say tomato. We're talking about the same thing. Good. Okay. Why do we need this? This is going to come back and play a role in certain cases. Last time we fit and we had the characteristic equation of an autoregressive model, right? The roots of it ended up being complex, correct? So when you have complex roots, there is going to be a period of some sort. You've got to pick that up too. If it is a dominant frequency, you can't ignore it. Good? Okay.